Temperature necessary for removal of nuclear spin entropy. Consider any solid such as silver whose nuclei have spin. The magnetic moment of each nucleus is of the order 5 times 10 to minus 24 ergs per Gauss, and the spatial separation between the adjacent nuclei is of the order 2 times 10 to minus 8 centimeters. No externally applied magnetic field is present. Adjacent nuclei can interact, however, by virtue of the internal magnetic field B internal produced by the magnetic moment of one nucleus at the position of a neighboring one. Estimate the magnitude of B internal by using your elementary knowledge of the magnetic field produced by a bar magnet. So let's start with this. So first of all, we have a magnetic moment of each nucleus 5 times 10 to minus 24 ergs per Gauss. I'm going to do this calculation in CGS and then convert to SI, and I will explain the reason why. The distance between nuclei is 2 times 10 to minus 8 centimeters. So what happens is you have two nuclei at this distance r between them, and the magnetic field produced by this one, let's call this 1, 2, magnetic field created by 1 acting on 2, magnetic field on 2 due to 1 is the B internal. Okay, so we're going to estimate how much this magnetic field is. So I'm just showing this direction for demonstration purposes, so that's not necessarily the direction of the magnetic field. Now, first of all, I want to use my elementary knowledge of the magnetic field produced by a bar magnet. So what is the magnetic field produced by a bar magnet? So let's calculate the magnetic field due to a magnetic dipole. Now, the dimensions of the nucleus is of the order of femtometers, and the distance between them is of the order of angstroms. So we have orders of magnitude difference. So it appears that the magnetic field due to the nucleus will be due to a point-like magnetic dipole at a very high distance. So if I have a bar magnet, so let me exaggerate this. If I have a bar magnet like this, and I have the North Pole on one side and the South Pole on the other side, I call the pole strength plus P, and here the pole strength minus P. So P is the pole strength. Now, if I want to find, given that these poles are at a distance L from each other, first of all, the magnetic dipole moment due to this configuration is M, magnetic dipole moment, is basically the pole strength P multiplied by L, the distance between poles. Okay, so now I want to find the magnetic field at a distance r from the center of this magnetic dipole. So I'm at a distance r. So what I need to do is to look at the components of the magnetic field due to the South Pole and due to the North Pole that will be created at this point of interest. So this is my point P. Well, the magnetic field created by the North Pole will be in this direction, and the magnetic field created by the south pole will be in this direction. So the south pole magnetic field points towards the south pole, the north pole magnetic field points away from the north pole, and if you complete this triangle here, this is L over 2, L over 2. I'm looking at a radial distance r from the center, and so this is the capital R distance between the poles and point P of interest. So you can see that if you complete this triangle, this angle is theta, this angle is theta, the magnetic field at this point will be pointing in this direction. This will be H, the magnetic field, and it will be equal to the magnetic field due to the north pole multiplied by sine theta, and magnetic field due to the south pole multiplied by sine theta. So basically sine theta is L over 2 capital R, you can see here, and the magnetic field created by the pole is a single pole is equal to P divided by capital R squared. So that's H plus and H minus, P divided by capital R squared. So I find that this is PL divided by R cube. So magnetic field H due to a pole strength P is P divided by the radial distance R squared, R distance from the pole. So this is all in CGS. So you can see that this is the magnetic moment M divided by R cube. Okay, so you can see that this R square from this triangle is L square over 4 plus R square, and if R is much greater than L, as in the case of the nuclei here, femtometers versus angstroms, we have R approximately equal to small r, and therefore the magnetic field due to internal field due to a magnetic dipole will be given by magnetic moment divided by R cube. Okay, so this is our elementary knowledge of the magnetic fields. Now, if I substitute the numbers here, the magnetic dipole moment of each nucleus is 5 times 10 to minus 24 ergs per Gauss. So it is 5 times 10 to minus 24 ergs per Gauss divided by the distance in centimeters, 2 times 10 to minus 8 cube. You can see that the answer will be 0.62 Gauss. And if you want to work in SI, so 1 Tesla in SI units is equal to 10 to 4 Gauss. Gauss, this is in CGS units. So you can see that the magnetic field B internal is 6.2 times 10 to minus 5 Tesla. So let me put a remark here. So if you try to convert these units to SI units to start with, so if M is equal to 5 times 10 to minus 24 ergs per Gauss, that is equal to 5 times 10 to minus 27 joules per Tesla. And remember, 1 joule is equal to 10 to 7 ergs. We can also write R 2 times 10 to minus 8 centimeters as 2 times 10 to minus 10 meters. The magnetic field you will calculate is going to be given by, in SI units, the conversion between the magnetic field H that we calculate this way and the magnetic field in SI units is mu 0 over 4 pi multiplied by 5 times 10 to minus 27 divided by 2 times 10 to minus 10 cube. So mu 0 is 4 pi 10 to minus 7 Henry per meter. That is the permeability of free space. Okay, and this comes from the fact that the magnetic field H in SI is defined as the pole strength P divided by 4 pi r squared rather than P divided by r squared here. This is CGS, this is SI, and the relationship between magnetic field in SI and H in SI is that magnetic field B is mu 0 times H in SI. So mu 0 over 4 pi factor comes from this. So this is just a technicality of conversion between units. Okay, so let's look at part B of the problem. Now that we know the magnetic field created by the nuclei, how low must the temperature of the solid be so that a nucleus subject to the magnetic field be internal due to its neighbors has significantly different probabilities of pointing in opposite directions? Okay, so let me take a look at the probabilities. So probability of having a positive magnetic moment, P plus, is a constant C times the energy associated with it, e to the minus beta mu 0 bi. So if the magnetic field, so this is the corresponding energy is equal to mu 0 bi. So I have the magnetic moment pointing in opposite direction. So mu 0, this one is not permeability of free space, so be careful with this one. Mu 0 was given as 5 times 10 to minus 24 ergs per Gauss, remember. So this mu 0 pointing in the opposite direction to Bi. So it has the energy plus mu 0 Bi. The probability is C times e to the minus beta energy, remember. So it is given by this expression. And P minus, on the other hand, would be given as C times e to the beta mu 0 Bi with the corresponding energy E minus being minus mu 0 Bi. This is mu 0 pointing in the same direction as B internal. Okay, and I noticed that mu 0 times B internal divided by KT, this is beta times mu 0 B internal. If you look at this number, mu 0, 5 times 10 to minus 24 ergs per Gauss, and then so I have converted it to SI units. It's 10 to minus 27 joules per Tesla, multiplied by the magnetic field 6.2 10 to minus 25 Tesla, 27 25 divided by KT, and this is for um, basically all typical temperatures you can think of, the thermal energy is of the order of, um, so let's check for T is equal to TR, this beta, beta mu 0 Bi value would be 5 times 10 to minus 27, 6.2 times 10 to minus 5 divided by 0.025 milli electron volts, 1.6 10 to minus 19. So you can see this would be 2.5 10 to minus 2. 10 to minus 19 would give us 10 to minus 21. So this number is small. It's much less than 1. Okay? So I can use a Taylor series expansion. So I can write P plus as approximately C times 1 minus beta mu 0 Bi, and P minus approximately as C times 1 plus beta mu 0 Bi, because e to the x is 1 plus x when x is much less than 1. So I can use this Taylor series expansion. Okay, so the probabilities should be normalized. P plus plus P minus should be, it's equal to 2C in this case. So C times 1 minus beta mu 0 Bi plus C times 1 plus beta mu 0 Bi. This should be equal to 1, which means 2C is 1, or C is 1 over 2. So I can see that the probability P plus is 1 over 2, 1 minus beta mu 0 Bi, and I want this probability to be approximately 0, so that probability of pointing in the other direction is approximately 1. Why am I doing this? Because I want to have significantly different probabilities. So significantly different probabilities. That's my aim. So if you have 1 minus beta mu 0 Bi equal to 0, this means that beta times mu 0 Bi, we are asking to be 1, and that is Kt is equal to beta times mu 0 Bi, and in that case Kt will be equal to 5 times 10 to minus 27. So Kt is equal to mu 0 Bi. Kt is 5 times 10 to minus 27, 6.2 10 to minus 5 joules. And on the other hand, Ktr is 0.025 electron volts times 1.6 10 to minus 19 joules. If you take the ratio of these two, you can see that T divided by Tr is equal to 7.75 times 10 to minus 11, and room temperature is roughly 295 Kelvin, and with that I get a temperature roughly 2.3 times 10 to minus 8 Kelvin. Okay, so it has to be a very, very low temperature. So one thing here, I have assumed beta times mu 0 B to be much less than 1, and I have checked that value here for a temperature that is close to room temperature. This is much less than 1, let's say, but for a very low temperature, that's no longer going to be the case. So if you want to be more precise, you can go back to basically the original formula for P plus, which is c times e to the minus beta mu 0 bi, and set that equal to 0. So that would give you beta times mu 0 bi should be very close to infinity, right? So for that to be equal to 0. But on the other hand, if I use this approximation, I find that it has to be equal to 1. So this is an approximate answer. So basically, we haven't used the exact probability distribution to do this calculation. So this is an approximate answer for the temperature, but it has to be very, very low. That is the conclusion. So part C, estimate numerically the magnitude of the absolute temperature below which an appreciably non-random orientation might be expected. So how do I interpret appreciably non-random? Well, so for non-random orientation, if it's a random orientation, the probabilities would be 1/2. For non-random orientation, I would ask for a critical probability value of p minus equals to close to 0.51. Okay, so if it is 0.5, because I have a random distribution. So p minus is equal to 1/2 1 plus beta mu 0 bi, and I want this to be equal to 0.51. So this means beta times mu 0 bi should be equal to 1.02 minus 1, 0.02. So I have kt is equal to mu 0 bi, so beta is 1/kt. Kt is equal to mu 0 bi divided by 0.02, which is 5 times 10 to minus 27. Bi is 6.2 10 to minus 5 Tesla divided by 0.02. On the other hand, I have KTR is 25 10 to minus 3 electron volts, 1.6 10 to minus 19, then it becomes joules. I take this ratio again, and I find that the temperature T/Tr is 3.875 10 to minus 9. Room temperature is roughly 295 Kelvin. So this gives me a temperature of 1.1 times 10 to minus 6 Kelvin. Roughly. So again, because I'm using this approximation, so this is an approximate answer. So anyway, so in order to break the entropy of the nucleus, we have to go down to microkelvin temperatures, and in order to have a significantly different probability for one orientation, we need to go down to almost a nanokelvin range, so 2.3 10 to minus 8 Kelvin. So let's review what we said. We're considering any solid whose nuclei have spin, and the magnetic moment of a nucleus is 5 times 10 to minus 24 ergs per Gauss. Distance between nuclei, r, is 2 times 10 to minus 8 centimeters. There is no external magnetic field, so B external is 0. So they create a magnetic field on each other, and we're estimating the magnitude of this magnetic field that they create. So magnetic field due to a magnetic dipole, basically we can calculate the magnetic field due to a single pole as P divided by R squared in CGS units, where R is in centimeters. And if you consider the magnetic field due to the North Pole, which is pointing away from the North Pole, and due to the South Pole, which is pointing towards the South Pole, multiplied by sine theta, gives me the total magnetic moment at a distance r from the center. So that gives me, with the approximation that r is much greater than the distance between the poles, a magnetic moment m divided by r cube. This is in CGS, and if you calculate this, you obtain 0.62 Gauss, and 1 Tesla is 10 to 4 Gauss, so it's 6.2 10 to minus 5 Tesla. If you started out with direct conversion of the magnetic moment and the distance to SI units, then you would have to remember that the magnetic field in SI is mu0 over 4 pi, the H field given in SI, it's mu0 times the H field given in SI, but the H field is calculated as the pole strength divided by 4 pi r squared. So there is a factor of mu0 over 4 pi up front. Okay, so if you use this mu0 4 pi 10 to minus 7 Henry per meter permeability of free space, we would get the same answer. So it's better to do the calculation in CGS and then convert to SI in this case. The probability, I want the probabilities of the of pointing in opposite directions to be significantly different. So I'm looking at one extreme case where the probability of one orientation is 1, the other one is going to 0. So the probabilities basically will be given by canonical distribution. So this is one nucleus in thermal contact with the rest of the solid. We have a small system in contact with a large heat reservoir, so that's the case. And this beta mu0b value for a typical KT at room temperature is much less than 1. So I have used the approximation for P plus and P minus as C times 1 minus beta mu0b and 1 plus beta mu0b. And the total probability should be 1, so C should be 1/2. Now I want this probability P plus to be almost equal to 0, which means beta mu0bi should be equal to 1 in that case, and that gives me a temperature of 2.3 10 to minus 8 Kelvin. On the other hand, if I want a non-random configuration, break the entropy, removal of the nuclear entropy, appreciably non-random orientation, that would mean I want one orientation to have 0.51 probability, for instance, and 0.49 probability for the other one. So I have used P minus equals to 0.51, and I estimate a temperature of 1.1 10 to minus 6 Kelvin in that case.